A molecular equation gives the whole reaction. A complete ionic equation represents all strong electrolytes as ions. So strong acids, strong bases, and soluble salts will all be broken apart with charges. And then a net ionic equation includes only the components of the reaction that undergo a change. So here we're going to write the molecular, complete, and net ionic equations for when aqueous potassium chloride is added to aqueous silver nitrate to form a silver chloride precipitate plus aqueous potassium nitrate. So our molecular equation is just writing the components as they are. So we have potassium chloride. So potassium has a +1 charge, chloride is just Cl with a negative. So we get KCl, and that's going to be aqueous. Plus, then we need our silver nitrate. So silver is a +1, nitrate is NO3 with a negative. So AgNO3, and again that was aqueous. We form silver chloride. So silver, we'd already said, was Ag with a plus, and chloride is Cl with a negative. So AgCl, and it says it's a precipitate. A precipitate is the solid. So we didn't need to look at our solubility rules, but had it not told us it was a precipitate, we would look at our solubility rules to figure out if that was soluble or insoluble. Potassium nitrate, we have K with a plus and nitrate with a -1, so KNO3, and that was also aqueous. At this point, we could balance it, and in this case, it actually is already balanced. So now we're going to go and do the complete. When doing the complete, everything that dissociates should be shown broken apart with a charge. You can just put K with a plus, or you can put K with a plus with an AQ. All of our ions are always going to be aqueous, so I'm going to leave off the AQ just for space sake. But you should know that the potassium ion and chloride ion are both aqueous. We can't have ions that aren't surrounded by water. Plus, and then we're going to break apart our silver nitrate. Silver chloride's a solid. All solids, liquids, and gases are going to come down as they are. Make sure that you're putting charges and that they're the correct charges. That's one of the most common mistakes in doing net ionic equations. Next, we're going to cross out our spectator ions. Spectator ions are the ones that did not change. They look exactly the same on both sides. Potassium ion didn't change, and nitrate didn't change. Again, the ones that we're crossing out are spectator ions. For your net ionic, you're going to bring down everything that's left with the charges and make sure that you balance. If it's not balanced, it will be incorrect. In this case, I have one chlorine, one silver, and one silver. So this is correct. Also, make sure that you have charges on your chloride and silver on the reactant side. The last thing that we're going to do is draw the before and after. So when drawing it, there's a couple of ways we can do it. In this example, let's say that we just have 2 of each of the reactants. So we have 2 potassium chlorides and we have 2 silver nitrates. So our potassium chloride would be dissociated. So we'd have potassium broken apart and our chloride broken apart. And that would be floating around in solution. And then if we had 2 silver nitrates, we would have silver and nitrate. Nitrate's a polyatomic ion, so it stays as NO3. And again, in this example, I just said draw 2 of each of the reactants. Now we're going to draw as many products as we can. Well, one of our products is silver chloride, and it's a solid. So our solids should be together and on the bottom. So we've used one silver and one chloride up. And now I need my potassium and my nitrate, but it's still aqueous. So I have one potassium and one nitrate. Notice that I have more reactants, and so I've got to draw those on the product side. So I can make another silver chloride. And it's still together because, again, it's a solid. And I should also be able to draw another nitrate and another potassium. Notice I've used all of my reactants up. And my spectators were floating around. They're still just floating around. They haven't changed at all. Only the silver and the chloride have hit each other and then went to the bottom as a precipitate. Go ahead and pause the video and do the molecular equation. Restart when you're done. Go ahead and balance the molecular equation as well before restarting. So this should be your molecular equation. I went ahead and balanced the molecular equation because there's two ways we can do the net and our complete. First is if we balance the molecular equation, then we can keep that balancing all the way through. And we can say that we have 3 K ions plus 3 hydroxide ions plus 1 iron and 3 nitrates. Our iron 3 hydroxide should stay together. And then we have 3 Ks and 3 nitrates. When we cross out our spectators, notice that we have 3 on each side. If we had 3 on one side and only 1 on the other side, we've messed up balancing. You're going to cross out all of an ion. You can't be left with just some of the ion. And then 3 nitrates and 3 nitrates. So then my net ionic would be this. Had we not balanced the molecular equation, then we would have just balanced the net. And if I was to write out the complete, I could have just said that I had K and hydroxide. And then when I was doing my iron 3 nitrate, I would have made sure that iron had a +3, but then I would have just put 1 nitrate down here since I wasn't balancing until the very end. And then I would have kept this one together. And then I would have just said that I had 1 K and 1 NO3. So then I would have crossed out my K still, I would have crossed out my nitrates, and then I would have had 1 hydroxide, 1 iron, and 1 iron 3 hydroxide. So then I would have still wound up with the same net because I would have balanced it at that point. So that's how you would do it if you wanted to balance the molecular or if they gave you a balanced molecular. And again, just making sure that your ions are equal on both sides. So for drawing our picture, in this case, let's do it a different way than just saying that we have 2. So if we're to draw the picture, we can also look at our molecular equation and say, well, I have 3 of these and 1 of those. So let's start with 3 potassium hydroxides and 1 iron 3 nitrate, just so it works out perfectly and then we don't have extra of our reactants and products. So our potassium hydroxide should be broken apart and we should have 3 of them. And then we should have 1 iron 3 nitrate. When it breaks apart, I should have 1 iron and I should have 3 nitrates. So go ahead and draw the after beaker on your own, then restart to check your answer. You should have drew the iron 3 hydroxide together on the bottom, and I'm going to circle that to show that it's all together. So I've used my iron up and I've used 3 of the hydroxides up. So now I have 1, 2, 3 Ks and 3 nitrates still. If we look at our balanced equation, that makes sense. I had 3 KOHs reacting with 1 iron 3 nitrate to produce 1 solid, and then I still have 3 potassium nitrates. And because it's aqueous, it's still floating around. Notice that the spectators don't leave the container. They just aren't participating in the reaction. Their purpose is to bring in the hydroxide and the iron. Go ahead and pause the video, write the molecular and the complete, and go ahead and balance both of those as well. So restart when your molecular and complete are done. All right, so on this one, you started with acetic acid. Acetic acid is a weak acid. If you're given acetic acid, it's going to say that it's aqueous because it is technically aqueous. But the majority of it does stay together. So your weak acids and weak bases many times will be shown as aqueous. But if you're writing the molecular equation, you can say that it's a liquid just as a reminder that it's going to stay together. Because the state symbols aren't graded, the state symbols are there to help you figure out what stays together and what breaks apart. So again, acetic acid is aqueous, but because it's a weak acid, it will be shown together in our net ionic, which means that if you put it as a liquid, it may help you realize that you should not be breaking that apart. While potassium hydroxide is a strong base, so that should have broken apart. Potassium acetate is a soluble salt, so that should be aqueous. And H2O is a liquid, and so that should stay together. So this is what you should have for your complete ionic. Make sure that you have charges on your potassium, your hydroxide, and your acetate. So these 4 should have charges. So for the net ionic, in this case, we only have 1 spectator, and that's potassium. Don't forget to make sure that your equation is balanced. In this problem, it is already balanced though. Go ahead and draw your before beaker. Let's go with the same method that we did a second ago, and looking at our balanced equation, we have 1 acetic acid and 1 potassium hydroxide. So let's go ahead and just draw 1 of each of those in the before beaker. Restart when you're done. Acetic acid was a weak acid, so you should have had that together. And potassium hydroxide is a strong base, so that should be broken apart. So go ahead and draw your after beaker now. And in this case, we don't have anything really at the bottom of the container. We have water that's all around because it's a liquid. We had acetic acid, which is a liquid, so if we want, we can circle that as well. And so really just the acetate and hydroxide swapped partners in the net ionic. And then we can see that potassium was floating around. It's still floating around, so that was our only spectator. Go ahead and pause the video and do your molecular and complete and net. So go ahead and go all the way through and finish molecular, complete, and net. Make sure that you balance. Restart when you're done. So ammonium chloride should have broken apart. Sodium hydroxide was a strong base, so that should have broken apart. Ammonia, which was NH3, was a gas, it said, and since it was a gas, it should have stayed together. H2O is a liquid. You could have also said H2O was a gas or solid, but regardless, it's going to stay together because it's molecular. And NaCl is aqueous. So our spectator ions were sodium and chloride, and so we were left with ammonium plus hydroxide go together to make ammonia and water. Go ahead and draw your before reaction. Like the last 2 times, let's go with the balanced equation and just say that we have 1 of each. Restart when you finish the before reaction. So our before reaction, everything's broken apart, and go ahead and do your after reaction. So NH3 is a gas, so I would have it near the top or at least in the solution. H2O, again, a liquid, so it's just in the solution. And then we have our sodium and chloride ions floating around. So nothing's really a solid, so nothing's at the bottom, but as long as you had NH3 and H2O together in the container, then that is fine.